Hey, thanks to everybody on the Zoom conference tonight, the live stream over on our YouTube channel. If you haven't subscribed, please do so. If you like the talk, please give it a thumbs up. And of course, everybody that came from Meetup too. Well, let me tell you a little bit about our speaker tonight. Dr. Nour Raouafi is an astrophysicist, and he's also a principal professional staff member at the Johns Hopkins Applied Physics Laboratory down in Laurel, Maryland, and the project scientist, the reason that we're all here tonight, of NASA's Parker Solar Probe mission. That launched back on August 12th of 2018 and is currently the record holder of the closest man-made object to a star, our sun, and amazingly, the fastest man-made object with a top speed so far of 101 miles per second. And that translates to 364,621 miles an hour. But by 2025, it should be cruising over the sun at 428,000 miles an hour. Staggering numbers, it's crazy stuff. Dr. Raouafi collected his Ph.D. in December of 2000 from the University of Paris. And before joining the Johns Hopkins Applied Physics Laboratory in 2008, he was also working at the Max Planck Institute for Solar System Research and the National Solar Observatory. It is with great pleasure today, and Franco, thank you for inviting him, Dr. Nour E. Raouafi. Dr. Raouafi, welcome.
Oh, thank you so much for the invitation. It's great pleasure to be with you tonight to talk to you about one of the most amazing missions in NASA's history, Parker Solar Probe. Let me share my screen and I'm waiting. Okay, do you see the good view or the bad one?
We see an inset view with your thumbnails and a larger image.
You got to go to presentation mode.
Okay.
And then flip the screen. Use the exchange it.
Okay, it should be the good one now.
Perfect.
Okay, excellent. So I'm going to talk to you a little bit about Parker Solar Probe and what we are learning from it. And as you know, Parker Solar Probe launched in 2018. It's been over 3 years and a half now in space, and it's orbiting the sun. As I mentioned, what we are learning from the mission is just mind-boggling. It's just amazing what we are finding, and also it's overwhelming with the amount of the data and the quality of the data we are getting. It will take us years and years and years to make sense of all the data we are getting. But let me start far away from the sun. So this is a shot from Hubble, and I can tell you that in just a few months, probably we'll be looking at something way better than this through James Webb, and it's going to be amazing. But through this deep field from Hubble, what you can see here, there is a ton of stars out there, and there are plenty of galaxies as well. And whenever I see a picture like this one, it reminds me when I was a small kid. I was born in the countryside. We didn't have much light pollution at the night, in particular in summer. And you have a sky that is also full of stars. And I still remember vividly the question I always asked myself, and I didn't say it out loud, but I always asked myself is, what is going on out there? What are these things that are bright, and there are so many of them out there? And that question lives with me, and I believe it lives with many of us throughout our lives. It's just us humans that are so inquisitive, and we want to know what is going on out there. And talking about stars, and we are so fortunate to have a gentle star in our neighborhood that we can live in harmony with. That is our sun. And first of all, it is the source of life on Earth, and we are grateful for that. But it's also, as I mentioned, it's gentle, that we can start in so much detail. And whatever we learn about the sun, we can project it on other stellar systems that we cannot observe closely. And Also, the sun is so particular that it has a habitability zone, and one particular planet that is our Earth that harbor life, that is us and other creatures. And again, observing how the sun interacts with the planetary system, in particular Earth, in that habitability zone, will teaches us about what is going on in other stellar systems, where they have also planets around them, and they have some of them, they are in that habitability zone. And ultimately, the question that probably in the mind of all of us, of all of humanity, is, are we alone in the universe? And that's actually what probably pushes so many of us to try to search and understand systems out there in the universe and see what is going on there. And by the way, I enjoyed all the pictures you showed earlier. And before being a solar physicist, I was a stellar physicist. I started with the stars that are far, far away, but after that I drifted to the sun, which is anyway. When we look at the sun, and in particular the solar corona that we see during total solar eclipses, even when the sun is very quiet, there are basically no active region during solar minima, the solar corona is still very complex. And that complexity you are seeing all over the place, it is reminiscent of the complexity of the physics, of the physical processes that are ongoing there. And these physical processes are responsible for phenomena that are that resist any attempt to understand them for decades. And I will give at least 3 examples of this a little later. Now, the big question is, why do we care? We are here on Earth, we have our life, we are protected by our shield, that is the Earth magnetic field. Why should we care about studying the sun and the solar atmosphere in particular? The answer is very simple. Whatever happens in the solar corona in particular can affect us in many ways. It can affect space equipment like the ISS, GPS, communication satellites. I'm pretty sure you heard a few weeks ago that SpaceX lost about 40 satellites due to a solar event. I see my camera frozen. Do you hear me out there?
Yes, we can hear you.
Okay, excellent. Okay. So the effect of solar activity can reach us even in the ground here, through the power lines, and also the pipelines, agriculture, everything. And that is why we have to understand the solar corona. And let me give you one example, a couple of examples actually. And this is amazing. This is an event that occurred on March 13th, 1889. And you see the power outage in the Northeast Canada in the US. Imagine that we have a much bigger event that erupts on the sun, and it's heading toward Earth and hits Earth head on, and it causes power outage almost all over the globe. It is almost sure that the losses, economic losses, will be in the trillions. There is also possibility that the world economy can collapse, at least in certain places of the world. There are certain countries that are so fragile economically, potentially their economies will collapse. And with the collapse of economy, usually there is social unrest. And if that happens, God forbid, we will be thrown back to the Stone Age. We will lose all the knowledge we gained over the decades, and we will not probably be enjoying the technological advances that we have now, just because of the what is happening on the sun. And again, that's why the interest in the sun and the solar corona in particular is so great. And let me mention again the example of the SpaceX satellites that were lost a few weeks ago. I cannot take it out of my mind, because it's something that we usually talk about space weather and shows movies like this one that are a little bit far in the past, but this one, we just lived it. It's so recent, and we should not probably be doing that at this age. Anyway,
Could
Let
anything
me,
save those satellites?
sorry.
Could anything have saved those satellites? Better preparation?
I think if they calculated the orbit a little bit better, the satellites will be safe. I think they planned to have the satellites in. First of all, they parked them on a low Earth orbit, and after that they are supposed to bring them higher, but they were just caught by the solar event while they were still low at that low orbit. So the drag from the Earth atmosphere was so big and just brought them down. So if they were a little bit higher, they should be fine.
Excuse me, can I just ask if your camera is on for yourself? Because we see your presentation, but we don't see you.
It is on, but let me try to launch it again.
Yeah, flip it. Maybe off and on may help.
Just give me a second.
There you go.
Is
Now
it
we can
better
see
now?
you again.
Okay, do you see me?
Yes, we do.
Because I don't see myself, so it's okay if I don't see myself.
Thank
Yeah.
you.
Yeah, and please, if you have any questions, stop me anytime. It's I prefer when there is a debate rather than a monologue. I like it that way. So let me go to these big mysteries that we discovered decades ago, but to this day we don't really understand them. And these are actually why we sent Parker Solar Probe to fly as close as possible to the sun, to give us that data that will help us understand this phenomenon. The first one is what we call the coronal heating problem. When you look at the solar surface, that is the photosphere that we see with our naked eyes, and you showed the picture earlier from about the active regions, and those, some of them are in the photosphere, some of them are in the chromosphere, but the temperature is not very high either way. So, but the temperature of the solar surface, it's, let's say, between 6,000 to 10,000 degrees. But you go a very short distance above, about 3,000 kilometers, and the temperature of the plasma will spike to more than 1,000,000 degrees Celsius. And that is counterintuitive, because from everyday experience here on Earth, if you have a source of heat, if you move away from it, it gets cooler. Obviously, that does not work for the solar corona. And let me give you one thing. The reason we discovered the coronal heating is not because we invented big observatories and we have better observations. Actually, the source of the discovery is actually an observation during a solar eclipse. That dates back to 1869, when two American astronomers, one of them went to observe that eclipse in Alaska, the other one was in North Canada. And independently, they made the same observation, and they actually discovered a new emission line that we call the green line. To this day, it's in the green part of the spectrum. And the mystery there is that we did not know what was the chemical element that was emitting that light. And that mystery lasted 70 years until we invented the spectroscopy of highly ionized iron in laboratory. And then we discovered in the late 30s, early 40s, that green line is actually emitted by iron ionized 13 times. You take an iron atom, it has 26 electrons, you strip away 13 of them, and you get that iron. And the mystery there is that these ions, the highly ionized ions of heavy elements, they exist only on very hot plasmas. And the very existence of iron 13 plus in the solar corona means that is millions of degrees hot. And that's how we discovered the coronal heating. But to this day, since we understood that solar corona is so hot, we don't really understand what causes that heating. The second phenomenon, which is also so puzzling, and it's closely related to the coronal heating, by the way, it's what we call the solar wind acceleration problem. The solar wind is a flow of charged particles, that is electrons, protons, and heavy ions, that are continuously flowing away from the sun to fill the whole heliosphere. And when you are low down at the base of the corona, these particles are almost standing still. Their speed is about 5 to 10 kilometers per second. But a short distance above, they start flying at hundreds of kilometers per second. And there, we don't understand where they get the energy from to get to this high speed. The third phenomenon, I think I talked a little bit about it earlier. It's explosive activity in the solar corona. That is flares and CMEs, coronal mass ejections. And whenever you have these events, they accelerate a certain population of particles to almost the speed of light. We call them energetic particles. And these are extremely hazardous to space equipment, satellites. They are hazardous to humans in space. If we want to send women and men to the moon and to Mars, hopefully in the near future, we need to protect them from these very particles because they are so damaging. They can cause cancer in no time at all. And also, again, they are hazardous for space equipment. And also, when we get big doses of them, they are the ones that causes these induced currents in the power grid, and usually they cause damage in the power grid. So these are the three phenomena that we want Parker Solar Probe to help us understand. But let me say this: Parker Solar Probe is primarily an exploration mission, in the sense that we are flying into a region of space that we never visited before. And whatever observations that we are making is new. And it's a potential discovery. And that's exactly what we are learning from the data. It's the data we are getting is a treasure trove. And okay, let me give you a little bit of history about Parker Solar Probe. The idea of sending a probe to fly close to the sun is not new at all. It dates back to 1958. Actually, it predates NASA. NASA was created after this date. And in that same date, this gentleman, Eugene Parker, made the prediction that the solar wind exists. And some scientists back then, they basically called him crazy, and he almost lost his job because of that. So there is, in 1958, on that same year, there is a Simpson committee which suggested 3 big missions that NASA has to implement, and one of them is Parker Solar Probe. It's actually number A here. Since then, there were multiple attempts to implement this mission, but all of them failed for 2 reasons. One of them is that we did not have the technology to protect the spacecraft when it is very close to the sun. The environment is so harsh, and if you don't protect your spacecraft, you will lose it. Or the other reason, the mission was so expensive that NASA cannot afford it. But in 2008, actually at EPL here, we came up with a new concept of the mission. Instead of going all the way out to Jupiter and fly so close to the sun and basically do one flyby by the sun, and the mission will be over afterwards, we changed it, and we are using Venus to I'll come to Venus in a minute, but okay, these are the different concepts over the years that were tried, most of them at JPL, but at EPL as well. But as I said, they did not succeed for one reason or another. But since 2018, Parker Solar Probe is reality. It's flying by the sun, and it's doing a marvelous job out there. How did we change the mission and make it happen? First of all, we had to invent new technology. You cannot have a spacecraft that fly close to a star without being able to protect it at any minute, at any second, at any fraction of a second. You have to protect your spacecraft all the time. And if we did not have this piece here that we call the TPS, the thermal protection system, this heat shield, we would not have a Parker Solar Probe. And I can tell you, the heat shield is just a piece of carbon foam. It's 4.5 inches thick, and it has a plasma spray on top of it that is white. When Parker Solar Probe is closest to the sun in 2024, that side facing the sun will be glowing at 2,500 degrees Fahrenheit. 4.5 inches on the back we will be only at 700 degrees. So we lost most of the heat within that 4.5 inches. And 1 meter behind, it will be room temperature. Also, you have to power your satellite, and we have to fly custom-made solar panels that are water-cooled, and that's the technology that is flown for the first time in space. It never happened in space before. And obviously, when you are, in terms of instrumentation for science, you have to fly your best instruments, the most sensitive ever. Now, how the mission came about, as I said before, instead of going to Jupiter and have a gravity assist and fly above the poles of the sun, and basically have one single flyby, and it's so deep in the solar atmosphere, and after that the spacecraft is done. Now we changed it. We are using Venus. We use Venus 7 times, and every time we fly by Venus, we get closer and closer to the sun. We do it in a gradual phase, and over 7 years we get where we want to, which is about 3.8 million miles from the solar surface, and we will do that on the December 24th, 2024. That is 1 day before Christmas. Let me skip this. This is the one I want to show, the solar cycle. So we launched Parker Solar Probe in 2018 when the sun was very, very quiet. It's deep solar minimum. But by the end of the prime mission in 2025, we will be at solar maximum. Imagine that we launched it in this minimum here in 96. By the end of the prime mission, we will be at solar maximum. But if the spacecraft is still healthy and everything is going well, we will keep the mission going. We don't want to stop it. Ideally, we want to get to the next minimum. That will be a full solar cycle. But the hope is to keep it going until we cannot drive it any longer. Now, what is the status of the spacecraft? We finished 11 orbits now, and we are at 5 million miles away above the surface of the sun. That's the closest distance that we achieved so far. And as you mentioned earlier, this is the fastest spacecraft ever flown in the close to the sun. Let me now go to the science discoveries, and there are so many of them, but I have just selected a few of them. And let me start with one that is historical. In 1929, there was a physicist called Henry Russell. He predicted that there should be a dust-free zone around the sun. And the dust-free zone means that there is a sphere, like a sphere around the sun, where there is no dust at all. But since then, people looked at it over and over again, and they could not locate it. Parker Solar Probe from Orbit 1 gave us the very first hint that this dust-free zone exists. And this is how we knew it exists. If you plot the intensity of the light scattered by dust, we call it the F corona, we get this curve, the red curve from Parker Solar Probe. Let me start first with the green curve. The green curve is what we see from 1 AU, and it's increasing all the way to the sun, meaning there is no dust-free zone, since the intensity is increasing all the way in. But what Parker Solar Probe showed us, that far away from the sun, the two curves coincide. But when we are very close, that intensity of the light scattered by dust start decreasing. That means the density of the dust itself, it's decreasing as well. And that's how we confirm that the dust-free zone exists. And now we know where it is exactly. So we have a paper that is under review, and we know that dust-free zone exists. And this is a historical discovery, and it's not really in the prime science of the mission, but still, it's so amazing. It tells us about dust dynamics when we are very close to the sun. And by the way, dust is so important in the plasma physics out there. Let me go to another neat observation. This one we did it. The way we achieved this, basically we have the imager that is looking to the side of the sun. We cannot look directly at the sun, so we look at one side. We flip the spacecraft 180 degrees, and we look at the other side. And if you follow this trail here, all the way, it passes by Venus. There is actually excess emission along this trail here. and that's not of coronal origin. It's not of solar origin. What we are looking at, in fact, is actually a dust ring along the orbit of Venus. You have Venus that is orbiting the sun, but along that orbit also, it's like you have a tube of dust particles. It's like a ring. And by the way, Earth has one as well, but this is the first time that we've seen that for Venus. And there is a mystery as well, how that dust ring formed. There are actually two theories. One of them tells us that that dust ring actually probably dates back to the early ages of the solar system. But the other theory tells us no, actually, when Venus is orbiting the sun, because of its because of the gravity, it traps dust particles in its orbits. But after that, obviously, due to collisions, they will be ejected from the orbits. So you have an equilibrium between trapping and ejection of dust particles. Let me go to the sun now. When we launched
can you speak to how dense are these particles, these dust particles? Is it dense enough they could actually pick some up and bring them back?
Oh no, it's very the density is so, it's higher than the background, but it's not really by much at all. It's not by much. It's probably 10% or something like that. But if you have a dedicated dust detector, then you definitely can measure the density much more accurately. But also you can measure the composition of dust, and that's one of the big unknowns. Because from data like this one, we cannot really make what is the composition of those dust particles.
Thank you.
You're welcome.
Thank you very much.
Sure. Let me go to solar physics now, a little bit more into solar physics. So when we launched Parker Solar Probe, it was in 2018. The sun was extremely quiet, like this movie here on the right. There was no active regions. There was no big CMEs. And we have one suite of instruments that is supposed to measure these high energy particles, the ones that are flying at a fraction of the speed of light. And the question that we were asking ourselves is, well, probably these particles will not observe anything until the sun wakes up. But to our big surprise, when we got very close to the sun, we started actually seeing tiny events, energetic particle events. When you are far away from the sun, you don't see them. They kind of get diluted. But close to the sun, you see them so clearly. And they have a lot of mysteries with them. If you look at this triplet that occurred within 48 hours, and you look at the composition of event 3 and 5, they have the same composition in terms of particles, but event 4 is completely different. And presumably they are coming from this same region here. That's a big mystery, why they have a different composition. And to this day, we don't really understand why is that. But let me tell you this, why these events are so important now. They are extremely important because they kind of prepare the ground for big events. They inject inject particles that at medium energy. It's not really the very high energy, but it's just medium energy in the solar atmosphere. That when the big events comes along, they just take them to the next step and accelerate them to almost the speed of light. So basically what they are creating a reservoir for the big events. And this is one of the big mysteries, because we don't really understand how these particles can be accelerated to these extreme high energies without having that medium step. And probably this is actually the explanation of that. And that mystery has been around for decades, but Parker Solar Probe is giving us the very first hints why that is happening. Let me now move to the big news that we announced at the AGU in December. And as you can see, this is a screenshot from Google I made a couple of months ago. And you can see Parker Solar Probe has been around all over the place in terms of press coverage around the world. And the reason for that is there are 3 things that we did in the same orbit, orbit 8. What we are seeing here is the movie of orbit 9. For the very first time, the spacecraft start flying through the structure we see during solar eclipses. those coronal structure we see during solar eclipses. And I'll tell you how we know that. Imagine yourself that you are driving in the highway and you have the signs. When they are far ahead of you, you see them basically at the same height. But once you get closer and closer to them, their height starts increasing, and at a certain point they will pass above your car. For Parker Solar Probe, when it's flying through coronal structures, some of them will be flying beneath, under the spacecraft, some of them will be flying above the spacecraft. And in terms of the how we know that we see that, focus on the upper part here and the lower part. At a certain point, you see structures moving upward, and on the lower part, you see structures moving downward. It's during those times that the spacecraft is flying through these structures. It's actually doing it right now. That's how we know Parker Solar Probe is flying within the solar corona, the immediate atmosphere of the star. That's how we knew we've done that. And this has been a big milestone, because forever we want really to get to the real atmosphere of the sun, where we want to get that data and explain the heating and the acceleration of the solar wind. The second evidence for that, we got it from the plasma measurements itself. There is a boundary between the solar corona and the solar wind. The solar corona, below that boundary, the magnetic field is so strong that basically everything rotated rigidly with the sun. But above that boundary, the magnetic field becomes so weak, and the plasma will fly radially, and it will carry the magnetic field with it. And crossing this boundary is so important to understanding the physics that gives birth to the solar wind. It gets it hot and it gets it accelerated. And we did that for the first time in April 28 of 2021. When we tried to locate what was the structure that we flew above, that where we crossed that boundary, it's what we call a pseudo streamer. Pseudo streamer is one of those bright structure in the solar corona that we see, we often see, but it has a special topology. The magnetic field on either side, on both sides, has the same polarity. And other streamers, they should have has opposite polarity, but for this one, it has the same polarity. And by the way, this is the orbit of Parker Solar Probe. It's not to scale, but it's more or less where we are flying above that structure. And where we cross that boundary, when we are in the middle of it, it's about right here. Now, imagine you have a hurricane, and you have your spacecraft flying through it. Actually, we crossed the boundary when we are flying through the eye of the hurricane. The analogy is kind of similar. It's there where we do it, and it's the density there of the plasma gets so low that the solar wind becomes subalvenic. That is what we call the alpha speed in the plasmas. And when above that boundary, the solar wind is faster than the alpha speed, but below that, it's below the alpha speed. Another big discovery from Parker Solar Probe is what we call the magnetic field switchbacks. And the magnetic field switchbacks, it's like a road in a mountain that has a lot of switchbacks, and that's exactly what we see in the solar wind. And you have this ripple on the magnetic field. It basically forms an S shape. This has been seen before far away from the sun, but you see one every now and then. They are so rare. But when we got so close to the sun, we saw a gazillion of them. And their importance comes from this fact. They are so energetic. They carry so much energy with them, and it's not really easy to maintain them in the solar wind. And remember, we are actually looking for energy sources to explain the heating and the acceleration of the solar wind. And these actually could be one of the phenomenon that will solve the big mystery about the coronal heating and the acceleration of the solar wind. Now, This is where it becomes so interesting using the switchbacks. When we got so close to the sun during the last few orbits, we can actually connect the in situ measurements of switchbacks to what is happening on the solar surface. We know where they are coming from. They are coming from the chromospheric network. And this is actually, you see this in the velocity. There is this cells, and the intercells, the network between the cells, is there where the magnetic field is concentrated. Let me move to the next slide. It will explain it better. So the magnetic field is concentrated within that intercells, and it forms what we call the supergranules. So here the field on the photosphere, it's so dense, it's located only in small areas, but obviously higher up in the corona, it opens up, it expands, it forms what we call funnels. And these funnels are not stable. There is a lot of magnetic field reconnection and waves, and obviously every now and then you will form disturbances like this one. It's like that's small switchback, and that will travel all the way out in the solar wind, and that's how we know where they are coming from. So through these switchbacks, we know how the solar wind is born. It's born actually through small scale magnetic activity. It's very tiny activity. It's small explosions in the solar corona that are everywhere, and they pop up small puffs of plasma in the corona. And that's how the solar wind is formed. This is just an animation, basically showing what I said before. You have the convection from the solar interior. It brings magnetic fields, but it concentrates them in these networks here. And in a little bit, you will see the funnels that are forming above, and within them you have this small scale activity that will create these switchbacks. Yeah, you see them now. They start flying outward. Now, let me move a little bit to planetary physics, and I hope this movie will play. Okay, it will play. So, as I said before, we use Venus to get closer and closer to the sun. That's the main purpose of flying by Venus. But obviously, whenever we fly by Venus, we have all our instruments turned on, trying to understand the induced magnetosphere of Venus. Venus does not have a magnetic field like Earth, but there is an induced magnetosphere because of the interaction of the solar wind in the Venus atmosphere. So it's not like the Earth magnetosphere, but still, it's interesting to understand what is going on there. And one particular observation we did several orbits ago, I think it was during the third Venus flyby after Encounter 5. For the first time, we flew behind Venus. The spacecraft had an eclipse of about 10 minutes, and we took images of the night side of Venus. And this is what we saw. We saw this structure here, this one here. We were so excited about it, and we thought that we saw the clouds in the solar atmosphere. To our disappointment, we realized that actually the same structure was observed several years ago by another mission, and there's actually a structure in the surface of Venus. It's actually a whole plateau of mountains in Venus. It's very high above the very high. And so, yeah, okay, it was fine. We observed that structure. I think we had quite a bit of coverage in terms of press about it. But for people like me who are solar wind physicists and also solar physicists, basically it stopped there. We thought, yeah, that's about it. But when I showed this picture during one of the seminars, and there were some colleagues who are specialists of Venus, and when they saw it, they were so excited about it. And they asked me, yeah, can we have the data? We want to have a look at it. And they made a big discovery out of it. And this is the big discovery that we found out. In fact, through those images, we discovered the thermal emission at the shortest wavelength ever detected from the surface of Venus. That is at about 700 nanometers. It's about here, 700, 750. This is actually the structures we are seeing. People usually they observe at around 1 micron. There was also observation at about 800 nanometers here, but Parker Solar Probe is opening a new window into planetary physics. And by the way, there are two missions that NASA is developing for Venus, and they are so eager for us. We have the 7 of Venus flyby. It will be in 2024, where we fly so close to the surface of Venus. We will be at 320 kilometers above the surface of Venus, and there will be an eclipse also there. So we are preparing, we are making plans to do as many observations there as possible. First of all, to see if we can make further discoveries about Venus, but also if we can help these missions probably target some new observations window that have not been known before. So Parker Solar Probe, in a way, it's so versatile. It tells us about the solar wind, about the sun, but also about planetary physics. And even there are other science we can do with Parker Solar Probe data. Other science that we do with Parker Solar Probe, obviously we do not have a dust detector on the spacecraft. But what we are doing here, we use the whole spacecraft as a dust detector. And in fact, Parker Solar Probe is bombarded by dust particles in the heliosphere. And we have electric antennas. Whenever you have a dust particle hitting the Parker Solar Probe, it created a small cloud of plasma. And that small cloud of plasma will create potential, an electric potential that will be detected by the electric antenna. And since we have 5 of them, we can locate the location and the direction of the dust particle hit, where it came from. And as you can see through orbit 1 to 3, we see only one peak of this dust particles. It actually occurs slightly before the perihelion. But starting from orbit 5, we actually see 2 peaks. There is one here. There is another secondary peak here. The first peak, we can explain it easily. There is no problem at all. There are 2 populations of dust particles. There are the alpha meteorites. These are orbiting the sun due to gravity. But there is also the beta meteorites that are due to collisions between the alpha meteorites. They get ejected out of the in the outer out away from the sun. That's actually the beta meteorites. And these 2 populations, they cause this peak. The big mystery was, what is this peak here? And this is it. When you have dust trails like the Geminids, and when they cross the zodiacal cloud, there will be interactions there. So these are actually the 2 populations of dust particles, the alpha meteorites and the beta meteorites. The ones in the arrows, these are the beta meteorites. But in a little bit, we'll see the Geminid dust trail. When it meets the zodiacal cloud, it actually deteriorates because of interaction, because of collisions. And what it creates a stream of dust particles. That's actually what is causing that second peak. This is the very first time we see the deterioration of dust trails because of the interaction with the zodiacal cloud. We have never seen this before. And this can occur not only for the Geminids, but it can occur for the dust trails from comets. It can occur for any whatever is creating those dust trails. We can see this deterioration. It's so important also for the physics of dust in space. I'm almost close to the end now. We call this the portrait family, and in one image, we see 6 planets out of the 8 planets of the solar system. We see Mars here, Saturn, Jupiter here, Venus, Earth, and Mercury. Obviously, you see them in opposite order, angular order. The Sun is on the left here. And the way we saw Parker Solar Probe detected, made this picture, we were at the closest point to the Sun, at perihelion. And Parker Solar Probe was looking at the solar system from the inside out. So that's why you see Mercury the furthest, because it just, in terms of the angular position, it was the furthest in the field of view. Again, for us, this is a nice picture. It's amazing. But our friends who are doing exoplanets, when they saw this type of data, they were so excited about it. What they want to do with it is what they call exoplanet analog science. And so now we met with them, we developed programs with them that we will observe planets at different phases when they are orbiting the sun. And that way um, they can study planets around other stars when at different phases as well. I'm honestly not specialized in exoplanets, but it's amazing how data like this one that is almost useless to us in terms of science. I mean, I'm talking about solar wind people, but for other people, it's like a gold mine for them that they did not have it before, and it's amazing how a mission like Parker Solar Probe is so versatile. I think I will stop here, and I'll be happy if to answer any questions if you have any. And there are so many other things that it can take me hours to talk about them, but I will stop here and answer your questions if you have any.
Okay, we did have one question early on. Can you explain the fuel system for Parker Solar Probe?
We use hydrazine, and we launched the spacecraft with 82 kilograms of hydrazine. And the idea then was to use most of it immediately after launch. We have to correct for the orbit and put it on the right path to meet Venus a couple of months later. But we were so lucky that the launcher put us almost on the ideal spot for the orbit. So instead of using tens of kilograms of hydrazine, we used only 3 kilograms of hydrazine. And now what we have left on the spacecraft is 70 plus kilograms. And that can keep the spacecraft going for tens of years. If the other subsystem remain healthy, theoretically, we can keep Parker Solar Probe going for over 50 years.
Wow. Okay.
What's the chemical reaction? What is being thrown off of the hydrazine that's actually creating the thrust? Is it boiling? Is it breaking down? Is it creating?
Now, there is actually a chemical reaction that happens. It will create hydrogen. It will create water. It will create nitrogen, and there is another chemical. I think it's another molecule that has carbon in it. And this, when they, it's like thruster. When they expand, they will give thrust to the spacecraft. But we use these. We have only small thrusters on the spacecraft, and we use it only for small corrections of the orbit. These are not big thrusters at all. But to keep the spacecraft safe, we use momentum wheels. That's what we mainly use.
Thank you.
Franco had a question here. I don't know if he can speak. I think he can. He can just ask it himself.
Oh,
Franco?
yeah. I wanted to know if any of the images that are taken by the Parker Solar Probe are accessible to the public, and if they are, where?
Absolutely. We make all our data public 3 months after we bring them down. It takes us 3 months to work out through calibration and preparing all the data. But at the end of 3 months, we have different sites where we put them. The main sites are NASA archives. For the images themselves, it's on NASA, the SDAC of NASA. I can send you the links to them later if you want. And for the in situ data, it's another archive. So in situ and remote sensing, they have different archives. But you can also get all the data from the websites of the instrument teams. And we also have an EPL website, the gateway at EPL, where you can get the data as well. And they'll be happy to send you all the links to get the data.
Thank you. That would be great.
And if you need help to process the data, and we are happy to help.
Thank you. Thank you very much.
Okay, we have a question here from Mike Lyons, who says, I know this isn't your primary mission, but how did Parker manage to see surface features on Venus that no other probe has been able to see?
I think it has to do with the sensitivity of the instruments. Our instruments, since we are flying so close to the sun, we have to customize them in a way to the environment that we are going there. And also the type of observations we are making there, it's not like the ones you make from 1 AU. And that's how our instrument is probably more sensitive than the instruments flown before. It has probably also to do with being lucky, and when you are lucky and not necessarily looking for something that people know before that there is emission around 1 micron, and they were focusing on that emission only. But for us, our instrument is not really designed to observe around 1 micron. It's observed to observe at shorter wavelengths. So in a way, we were lucky. So we were not really looking for it at all. Yeah, it's and also being lucky that these data fell in the hands of people who understand Venus better than us, that they make sense of it.
Great.
Okay, thank you. We have a question here. How far out does the sun's magnetic field extend? And if it is far out, why does it extend so far?
Well, as I mentioned earlier, lower down the magnetic field is so strong, it basically dominates everything. But in the solar wind, when we are above that critical boundary, the magnetic field is carried by the plasma. And the solar wind will travel as far as the edge of the solar system. So that's the termination shock. That is at about 100 AU. That's how far the magnetic field of the solar system extends. By the way, we have 2 spacecrafts that already left the solar system. These are Voyager 1 and 2, and both of them actually crossed that boundary between the solar system and the interstellar medium. That's how we know how far the influence of the sun extends in its immediate space. It's about 100 AU or so. And just let me give you another piece of information. We are studying another mission here at the Applied Physics Lab. And this mission, if it happens, and hopefully it will see the day in the next decade or so. And the goal of this mission is to fly it as far as possible outside of the solar system. Maybe beyond between 350 to 500 AU. And that will give us the view of the solar system from the outside. And also tell us about that interstellar medium that we don't know what it is made of.
Very interesting.
Well, on a related note, what is the closest point you expect Parker to get to the sun?
Well, on the eve of Christmas in 2024, we will be at 3.8 million miles from the solar surface. So imagine that the Sun-Earth distance is a football field. Parker Solar Probe will be at the 4-yard line.
Wow.
It's so close.
You cook a hot dog with that. I don't see any other questions here. Alex, you see anything?
Nope. I just posted another message on YouTube in case anybody has any.
Just popped.
There's one in the Q&A.
Okay.
Will the polar circle over the sun?
Will the probe circle over the sun's poles?
No. And I mentioned at the beginning that the original plans for Parker Solar Probe is to go all the way out to Jupiter. And the goal there is to fly it above the poles of the sun. But with the new profile, with the new orbits that we came up with at EPL, we actually stay very close to the ecliptic. And we cannot go very far above the poles. But talking about the poles are so important. Observing the poles of the sun are extremely important. And for instance, we cannot explain the solar dynamo that creates the solar magnetic fields in the first place, and that creates also the solar cycle if we do not observe the solar poles. And again, we are studying another mission here at EPL. It's a constellation of spacecrafts, 4 of them. 2 of them will stay in the ecliptic, and 2 of them will be flying above the poles of the sun. And that will give you full coverage of the sun as a whole. Imagine that over the last several decades, we were observing the sun always from one viewpoint. And that is extremely limiting for a star that is magnetized and that is extremely active. Things are changing all the time. If you don't follow them in time, you are missing information. But with a mission like we call it the 4-pi, by the way, because it gives 4-pi steradian coverage. With a mission like that one, we will miss nothing. We will observe the sun as a sphere, and that will be a game changer, definitely.
Isn't there like a mission from the European Space Agency that goes around the poles?
It's solar orbiter. I oftentimes call it the twin of Parker Solar Probe. It does not get as close to the sun as Parker Solar Probe. It's, I think, the closest. The perihelion is about the orbit of Mercury, 0.3 AU. But they will get as high above the ecliptic, or well, out of the ecliptic, because the orbits go above and below the ecliptic, out of the ecliptic as high as 30 or 35 degrees. And that will give us a much better view of the solar poles. But again, those observations, they will give us better view in terms of imaging. But there are the observations that I was talking about. It concerns the solar interior. And you have to get higher to get that heliosysmic observations. Basically, it's waves that are traveling in the solar interior. And you to observe them, you have to get much higher to 60 or 70 degrees latitude. Solar orbiter will not get that high.
That's fantastic. Thank you.
You're welcome.
All right. Any other questions?
When the Voyagers passed through the termination shock, was it very sudden, or was it in a few days that it was noticed, or was it a prolonged?
No, it's a little bit prolonged, and you have to have different elements to make sense of what happened exactly. So there are the instruments that measure magnetic fields, that are instruments that measure plasma, and you have really to combine both information from all these instruments to make sense of it. Obviously, that medium also, it's not really a sharp boundary. It takes a bit of time to fly through it. But judging by the age of the mission, which is 40 plus years, it took a very short time to cross it.
Okay.
So it's, yeah.
Got another question here. My high school daughter is interested in science and engineering. How can she pursue a career like yours? What advice could you give her?
First of all, I would advise her not to. I oftentimes I got asked the question a little bit different. Some people say, okay, how can be like you? And I often tell them, don't be like me, be better than me. That's actually the message, that because we, in a way, with what we are doing now, we are paving the way for the younger generations to make way more important discoveries than the one we are doing. And the generations before us, they did the same thing for us. So it's just a natural continuation. I think she has to follow her heart. That's the best advice that I can give to anybody who wants to be a scientist, or and in terms of science, obviously, if your daughter is interested in the sun and heliophysics, I would be happy to have another solar physicist in the community. That would be fantastic. But there is, in terms of research, any science is amazing. If you ask me, for example, if I'm not a solar physicist, what I want to be, I probably would like to search to find a cure for cancer. That's probably the first priority for me. I would love really to. If I have another life, I would definitely do that.
Thank you for what you're doing now.
You're very welcome. Yeah, and it's to be honest with you, we are so fortunate. First of all, we do the thing that we love, but we get paid for it, which is amazing. It's just amazing. So.
All right, I have a couple other little quick questions here. One is simple. What is the rotation rate of the sun?
That's really an amazing question, and that's one of the things that I mentioned that mission, the 4-pi, earlier. It's one of the questions that we want to study with it. The sun is a ball of gas, and it's not like Earth. Earth is rigid; it rotates like a rigid body. Everything, every point of the sun rotates at the same angular speed. The sun does not do that. When you look at it, the equator rotates faster than the poles. So we call that differential rotation. And that's actually one of the reasons why active regions are created in the first place. When you start with magnetic fields that goes from one pole to the other, because of differential rotation, they will be distorted into the equatorial direction. And at a certain point, they become buoyant, and they will erupt into through the solar surface and create active regions. That's how the sun rotates. It's differential rotation. It's not, but still, that's what we see on the surface. We don't know how that changes when we go deeper into the sun, and that is really important for the solar dynamic. And that's what we want to do with a mission like the 4-pi, definitely.
Here's one I think I know a little bit of the answer. How can Parker go so fast using so little fuel? Essentially, it's falling, right?
Yes. I think the magic word is gravity. The closer you fly by a massive body, the faster you get. It's just Kepler laws. And the closer we fly by the sun, we get that gravity swing in a way by the sun, and we get faster and faster and faster. That's how we do it. But let me tell you one thing that we often don't talk much about it, but it's extremely important. Well, the sun is so massive. It has 99.98% of the total mass of the solar system. And you can imagine, okay, you can easily throw a spacecraft and let it fly toward the sun. It doesn't work that way. It's extremely hard to get a spacecraft to fly very close to the sun. And the reason for that is when you launch from Earth, you still have that rotational speed of the Earth. And getting rid of that is so difficult. For Parker Solar Probe, we did it the way we did it is actually launch it in the opposite direction as the orbit of the Earth. In a way, slow it a little bit down. And that's how it will deep toward Venus. It will go toward Venus. And when we fly by Venus, again, we use it to slow the spacecraft a little bit. It's a tiny bit, it's not much. But every time the spacecraft slows down, it will get closer to the sun.
Very interesting.
Okay. I have one more, and it's not really a question. When we had our practice session, you mentioned the precision of the alignment of the heat shield and how amazing that is.
Yeah.
I wonder if you could talk about that a little bit.
It is fascinating. Okay, when you are close to the sun, if you don't really watch your spacecraft, you will lose it in no time at all. The environment is not forgiving at all. It's so damaging over there because we get so much heat from the sun, and basically everything will not catch fire, but it will burn. So that heat shield has to be pointed squarely at the sun at all time. And obviously, the spacecraft can jitter a little bit here and there, it can wiggle a little bit, but the tolerance is a fraction of a degree. That's how precise it should be. If you imagine a whole circle is 360 degrees, Parker Solar Probe has only a fraction of a degree. The way we control that, we know how it is pointing to the sun at all times. We have different sensors, but 7 of them are in particular very interesting. It's basically 1 pixel, but we have 7 of them. And every time we detect the limb of the sun, the edge of the sun, they will send a signal to the avionics, the computers on top of the spacecraft, saying correct your orbit, and that's how we keep it all the time safe.
What about cameras that actually have to take pictures of the sun? I mean, do you actually have cameras that actually pointed directly at the sun? Because I mean, that might be protected too, right?
Yes, obviously, when we cannot have any optics that can look at the sun, because for obvious reasons they will not work. They will just burn. The only imager we have is we look at the side of the sun. That way, it's like observing a little higher than the edge of the sun, but all the way past Earth. That's the only imager we have in the spacecraft. We call it a heliospheric imager. But apart from that, we don't have instruments that look directly at the sun.
Okay,
yeah.
Thank you.
You're welcome.
Great.
I've got a question that a child asked me once at one of our public nights, and I didn't have a good answer for him. And it's, do we think that there's anything solid at the center of the sun, given all of the pressures and everything?
Yes, I think the pressure at the center of the sun is so high that the core is basically a crystal of protons and helium as well, helium a little bit. That's how we get protons so close to each other that will fuse and fuse into helium. That's actually the thermonuclear reactions that are ongoing in the core. That's how the theory tells us. Do we have? And then, by the way, when I say theory, I think everything points toward that. Because there are other observations of gamma rays and neutrinos and all that, they confirm that. But do we have observations that can sense the core itself, like the rotation rate? We talked about the rotation in the convection zone and how it is differential. We don't know how the core, that core, which is a big crystal at the center of the sun, how it rotates, and whether it has a magnetic field, like fossil magnetic field from the primordial cloud or not. We don't really know the questions of that. For that 4Pi mission, if NASA goes forward with it and gives us a lot of money, we can actually put instruments on top of that will observe what we call the gravity modes. The gravity modes, the source of the gravity modes is the core of the sun. And that way, we will know way more about the core of the sun than ever before. But coming back to your question, the core is like a big crystal of the protons and helium nuclei.
Interesting.
Yeah.
Okay. I think we should wrap it up.
So,
Thank you.
Covered a lot of questions.
Thank you
Thanks
so
very much.
Thank you.
Thank you for the wonderful lecture.
Thank you. Very much appreciated. It's a pleasure.
We appreciate your time.
No, it's a pleasure. It's really a pleasure.
Right.
All righty. Well, that's about it for this month. Supposedly we will be open for public night this Wednesday. So I hope we'll see some of you there. And that is all, folks.